Welcome to today's Explainer. We are diving straight into the absolute extremes of the cosmos, unpacking some of the most mind-bending recent discoveries in astronomy. We're talking about environments where the very laws of physics are pushed to their absolute breaking point, from the dawn of time all the way to the beating heart of our own galaxy.
I mean, think about it for a second. What if a star could literally hide a supermassive black hole inside it? It sounds like a total contradiction, right? A star produces light, and a black hole consumes it. But this seemingly impossible paradox is exactly the kind of cosmic mystery we're going to explore today.
So here's our roadmap for today. 1. Secrets of the cosmic dawn. 2. The black hole star. 3. 3 facts about Webb. 4. S301, the fast orbit. And 5. The fascinating 8% limit.
Let's start with Section 1, Secrets of the Cosmic Dawn. We're unveiling the early universe.
To really set the stage here, we've got to travel all the way back to the very beginning. The cosmic dawn is that critical window starting within the first 50 to 600 million years after the Big Bang. This is when the very first light actually emerged in the dark universe. And this is the exact era where the James Webb Space Telescope recently spotted something that totally baffled astronomers, these mysterious little red dots that defied all traditional explanation.
Now, because the universe is constantly expanding, figuring out distance and time is a giant, complicated puzzle. Astronomers use these advanced distance models so the Webb telescope can act like a literal time machine, letting us measure light that has traveled for over 13 billion years just to reach us. Moving to Section 2, the black hole star. It's time to solve the mystery of those little red dots.
So what exactly were these ancient little dots? Well, let's focus on one colossal object in particular, called MOM-BH1. Its dead giveaway is something called a Balmer break. That's a sudden, deep drop in a celestial body's brightness at very specific wavelengths, which is normally a trademark of much older stars. But the crucial point here is that MOM-BH1 had the deepest Balmer break ever recorded. When you pair that extreme drop in light with its massive energy output, it completely eliminated the possibility that this was just a normal star. It had to be something else.
The sheer scale of this discovery is honestly hard to wrap your head around. MOM-BH1 is a supermassive black hole, 100,000 times the mass of our Sun, but it is completely engulfed by a massive envelope of gas, effectively a star the size of our entire solar system. Finding out exactly why stars hide black holes like this gives us profound secrets about how early galaxies were formed. In fact, understanding how stars hiding black holes reveal secrets about the cosmic dawn changes pretty much everything we thought we knew about the early universe. This crazy hybrid object perfectly explains the immense energy in those strange light signatures we were seeing.
On to Section 3, 3 facts about Webb and exactly how the JWST acts as a cosmic time machine.
To fully appreciate this ancient cosmic dawn, we really need to understand the role of the Webb telescope. Here are 3 facts about Webb observations that make it an absolute game changer. Step 1, it detects those pervasive little red dots hiding in the early cosmos. Step 2, it is powerful enough to capture ancient light from just 660 million years after the Big Bang. And Step 3, it identifies those deep Balmer breaks to unmask these objects as black hole stars. You see, the telescope doesn't just take pretty pictures. It actually analyzes ancient light patterns to prove that these extreme structures existed everywhere in the early universe, even though they seem to have completely vanished today.
Section 4, S301, the fast orbit. We are racing around Sagittarius A star. Okay, so we're pivoting away from extreme mass in the ancient universe and bringing it right back home to extreme gravity and speed in our present-day Milky Way. We want to figure out why stars spin so fast in the most extreme environments. Welcome to the Galactic Center. Using an incredibly precise instrument called gravity on the VLTI observatory down in Chile, astronomers have tracked a star named S301. It is orbiting Sagittarius A star, which is the supermassive black hole at the center of our galaxy. Instead of a star hiding a black hole inside it, we're now looking at a star being wildly accelerated from the outside by a black hole's immense gravity. Because of that unbelievable gravitational pull, S301 is whipping through space at an astonishing 25,000 kilometers per second. Just let that number sink in. To really put that into perspective, that velocity is an incredible 8.3% of the speed of light. The fast orbit of S301 makes it the absolute fastest star ever known in the Milky Way. This extreme speed challenges our standard understanding of physics. It's traveling at a fraction of the speed of light simply because it's caught in this giant cosmic gravitational slingshot. If you need a more down-to-earth analogy for that kind of speed, think about this: 1.6 seconds. If S301 were traveling at its top speed right here, it could travel all the way around the Earth's equator in just 1.6 seconds. Literally, before you can even finish a breath, it has circled the entire globe.
Finally, Section 5, the fascinating 8% limit, where we test the very edges of Einstein's theories.
So why does this massive velocity matter so much to modern science? And exactly why does that 8% limit fascinate scientists so deeply? Well, S301 completes a full orbit around the galactic center in just 8.7 years. And during that time, it dives within a mere 12 times the Earth-Sun distance from the supermassive black hole. That is dangerously close in cosmic terms. But this incredibly tight, fast orbit is actually a huge gift to astronomers. It allows scientists to measure the rotation of the massive black hole directly, giving them a perfect natural laboratory to test the absolute limits of physics.
When we put these two extremes side by side, it is so clear how black holes dictate the universe's most intense environments. On one side, we have extreme mass, MOMBH1, an ancient hybrid star in the early universe swallowing a massive black hole. On the other side, extreme speed, S301, a modern star right here in our galaxy being accelerated to near-light speed by a black hole's gravity. Whether they're hiding inside giant stars or slingshotting them at impossible speeds, black holes completely run the show.
This quote from researcher Felix Meng really hits the nail on the head as to why all of this matters. He says, for the first time, we would be able to very directly measure the rotation of a massive black hole, which would be a crucial test of Einstein's theory. Unlocking the secrets behind this 8% speed limit helps astronomers actually explain the very rules of gravity and astrophysics that govern our reality. These extreme observations aren't just fascinating trivia, they are literally the key to proving or disproving how the universe actually works.
So I'm going to leave you with this final thought to ponder. As we keep uncovering these literal mind-bending extremes, from stars that swallow black holes to stars moving at fractions of the speed of light, what other impossible objects are still hiding out there in the dark? The universe is vast, and we are just getting started. Keep looking up, keep questioning the universe around us, and thank you so much for joining me for this explainer.